Let's continue looking at some substitution problems. Here I've got in number 6, x squared times secant x cubed tangent x cubed. And that looks kind of like a crazy integral, but intelligent u substitution can actually make it turn into something pretty manageable. So what I noticed, and if you caught the last video, I gave you a little tip on this. I noticed that the derivative of x cubed is 3x squared. And I notice here I've got an x squared. And so that means that I probably might want to let my u be x cubed. So let's just try that. So if u is x cubed, that means that du is 3x squared dx. And that means my integral becomes the integral of secant of u now times tangent of u. And now that x squared times dx, that can be replaced because if I divide this by 3, then du over 3 is x squared dx. So I can put my du here and my over 3 there. Now this is again where just some of your knowledge has to come in. The antiderivative of secant u times tangent of u is something we know. It's actually, that's the derivative of secant. So that must mean its antiderivative is secant. And then we replace the u with x cubed. So I'm not going to lie, you might have wondered how I did that. So how did I know what to let u be? It just takes some practice. Again, when you notice a function and a version of its derivative, or a constant multiple of its derivative within the problem, that gives you a sense of what to let your u be. Like in number 7, I said I have x times e to the negative x squared, and I notice that the derivative of negative x squared is negative 2x, so the power gets down to a 1x, and I see a 1x here. So I'm going to let my u be negative x squared, and therefore my du becomes negative 2x dx. And so now my integral becomes e to the u. And if I just move some of this down, if I divide both sides of this by negative 2, then I get that du over negative 2 is my x dx. So du over negative 2. And the antiderivative of e to the u is just e to the u. And so here's my antiderivative. Now this probably would have worked if you let u be x squared instead of negative x squared. You know, that's a small change, but it still would have worked. You just would have had to have taken the derivative of e to the negative u. I'm sorry, the antiderivative of e to the negative u. But it still should have worked out. So sometimes there's minor subtleties that can change depending on who you are and what you decide to do. But in general, is if you make the if you follow the basic principles, you should be good. Sometimes we have to do a little rewriting before we make a substitution. Like in number 8. So when you look at number 8, you think, well, maybe I can let the u be the 7x. But then you'd just be taking the antiderivative of cotangent of u, and we don't really know the antiderivative of that off the top of our head. At least I don't. And we would probably have to do some kind of change, you know, we'd have to rewrite cotangent in some way, or do some algebra or some trig identity to get it to look different. So that means that if a trig identity is what we're going to need, we might as well try to use it now. Cotangent, I know, is the same as cosine over sine. So I'm going to rewrite this integral as the cosine of 7x divided by sine of 7x. This gives me more options in terms of what I want to use for my substitution as well. And that cosine and sine are nice because they're related to each other via derivatives, right? The derivative of sine is cosine, the derivative of cosine is negative sine. So what should I let my u be? I'm going to let my u be the bottom. I'm going to let my u be sine of 7x. And I guess the reason I'm doing that and not letting it be the numerator is because when we take the derivative du, that ends up being 7 cosine of 7x dx. Again, that front 7 is because of the chain rule. If you let your u be if you let your u be cosine of 7x, you would get your derivative to have a sign in it, but that sign is down at the bottom. It's not up at the top, so it wouldn't substitute out nicely because the dx is up at the top and the sine of the 7x is down below. With the substitution I made, cosine of 7x and dx, they're on the same level there, so we want that to happen. That way a nice substitution can occur. So this integral now becomes, I got a u down here, cosine of 7x dx, well, that's just du over 7. So du over 7. And now the antiderivative of 1 over u is just natural log of the absolute value of u plus c, and that's just 1/7 natural log of our u, which was sine of 7x plus c. We got a similar issue here in number 9. Again, letting u be 2x wouldn't really help because you still are confronted with what's the antiderivative of 1 over cosine squared. That's not so obvious. You might say let's let the u be the cosine squared, but then when you find the derivative you're going to get a sine x out of that, and there's no sine x in this problem to substitute out. But let's try a trig identity. Maybe I'll let this be, I'll write it not as a fraction. So 1 over cosine squared is the same as secant squared. So maybe I'll write this as secant squared of 2x dx. And we actually do know the antiderivative of secant squared. The antiderivative of secant squared is tangent squared. So actually, because we only have that 2 to deal with, you might actually, you can let your u be 2x. So you could let your u be 2x. And this will all work out very nicely. Once you start getting good at some of these, you may be able to just do these by a little bit of a guess and check method. So let's do that instead. So let's just say, okay, I know that the antiderivative of secant squared is tangent squared. So it's got to be tangent squared of 2x here, plus c. Now, if that was the answer, if I take the derivative of tangent squared of 2x, that's secant squared of 2x times 2, but there's no times 2 above in the antiderivative, so or in the integral. So that must mean I must put a 1/2 here in order to kill off that 2 that emerges from the chain rule. So you can see we kind of worked through that one with some guess and check, and there's nothing wrong with that. You can do that as well. U substitution is just usually a technique to help if your guess and check methods aren't aren't refined, or you don't feel comfortable doing that. But yeah, that's a completely legitimate way to answer to evaluate that indefinite integral.